In our previous lesson, we discussed the concept of real numbers, and we talked that there were two things that we weren't able to do in the set of real numbers. One of them was to divide by 0, and the other one was to take the square root of a negative number. Now, the reason we can't take the square root of a negative number would simply be this. If we wanted to take the square root of -1, then what we would be looking for is what number squared would give us -1. And there's no number that when you square it, you're going to get -1. So because of a need, mathematicians defined a number to be this. And they defined that the square root of -1 would be equal to the number I. And with that, then that means that I squared is equal to -1. This introduced our set of imaginary numbers, which then all of these fall under the set of complex numbers. So if we look at this then, if we're wanting the square root of -36, then that's the same as the square root of -1 times 36, which would be the same as the square root of -1 times the square root of 36. And we've defined the square root of -1 to be I, and the square root of 36 would be 6i. Now, if this is true, then this means that 6i squared should be -36. Well, we know that we square each of those factors, so 6 squared is 36. I squared is -1, so we have 36 times -1, which would give us -36. So therefore, it would work out and it would be true. Now let's look at our definition then of a complex number. Our complex numbers is any number that can be written in the form of a plus bi. And when it's in this form, our a and our b are real numbers. So they come from the set of real numbers. And we call a the real part, and the bi we call the imaginary unit. So I is our imaginary unit. Now, if a number has, every number we know today is a complex number. If it only has the a part, that's pure real. If it only has the b part, then it's a pure imaginary. So they have special names if they're just pure real or pure imaginary. But every number is a complex number. So -8 plus 6i would be an example of a complex number. -8's the real part, 6 is the imaginary part. The number 3i is a complex number, but since it only has the b part, then it's a pure imaginary. 9 is a complex number, but since it only has the a part, then it would be a pure real. Uh, a complex number is simplified if it's written in the form of a plus bi. And when we write it, we always write the real part first, then we write the imaginary part. We're not going to write a number such as 2i plus 3. We would use our commutative property and switch it around so that it's in this standard form. So some examples of this, we would have 6 minus 5i. That would be a complex number written in standard form. 3 plus 2i would be a complex number in standard form. The square root of 5 plus 3i, or the number 4 plus 3i square root of 5. And we just put the I between the 3 and the square root of 5. That's still the b, 3 square roots of 5, but it just helps us to know to distinguish the I, just like we did with our variables. Now, two complex numbers are considered equal if and only if, so two complex numbers, a plus bi. My So a plus bi and c plus di are considered equal if and only if a equals c and b equals d. So the only way two complex numbers are going to be equal is if the real part's equal and the imaginary part's equal. Okay, we're going to look at doing our operations on our complex numbers, and we'll look at adding and subtracting, and then at our multiplying and dividing. Now, when we go to add two complex numbers, so if we want to add 5 minus 2i to the complex number 3 plus 3i. Okay, what we're going to do is we're going to add the real parts and we're going to add the imaginary parts. Now, before we do that, we need to remove our parentheses. So we have 5 minus 2i plus 3 plus 3i. We can only add the real parts, so the real parts would be 5 plus 3, and then we would add the imaginary parts, which would be the negative 2i plus 3i, which is going to give us 8 plus I. So we want to add the real parts and we want to add the imaginary parts. And you don't necessarily have to use the commutative property to get the real parts equal. But just remember, you only add the real parts and then you only add the imaginary parts. Now, if we wanted to do some subtraction, let's subtract 2 plus 6i minus 12 minus I. Now here it becomes very important that you understand that this is one number and this is a separate number. We're subtracting those. So I've put them in parentheses, and it's important that you go through and you remove those parentheses. So this would be 2 plus 6i. Then we're going to have to distribute that negative 1, so that would be negative 12 plus I. So it's very important to distribute the negative 1 there. It's just like subtracting a binomial. So then combining our real parts, we would have negative 10. Combining our imaginary parts, we would have a plus 7i. So when you go to add or subtract, you simply add the real parts and you add the imaginary parts. To do our multiplication, then we're going to use our distributive property just like we did with our binomials, or our polynomials. So if we have 7i times 2 minus 9i. Okay, we want to distribute this, so we would have 14i. Then distributing the 7i, we would have negative 63i squared. But earlier we talked that I squared was equal to negative 1. We know that I squared is equal to negative 1. That was the definition of it. So if we go through, we can replace our I square with a negative 1. So we're going to have 14i, then negative 63 times negative I will make that a positive 63. And it's very important. We'll never leave I written to a power uh, greater than 1. We'll always be able to simplify that down. If we were multiplying two complex numbers, in this last case we had multiplied uh, a pure imaginary times a complex number. So if we go through and we multiply two complex numbers such as 5 plus 4i times 6 minus 7i. Now this looks like multiplying two binomials like we've done previously, and that's what we're going to do. We're going to distribute. We're going to distribute our 5 to each one of these terms. So that would give us 30 minus 35i. Then we'll distribute the 4i, so that would be a positive 24i. And then distributing it to the last term would give us negative 28i squared. Okay, combining our like terms, we're going to have 30, then we have a negative 35 plus 24, so negative 11i. And then again, we've got negative 28i squared, which would then be the same as times negative 1. So we've got 30 minus 11i plus 28. And now we've got like terms that we can combine. So we have 58 minus 11i. But we will always simplify our I squared. It's a negative 1. Basically, if you look at it, what it does is it changes the sign of that term. Now, we have some special numbers that we can multiply, and these are called conjugates. And you deal with conjugates in several different areas. But the conjugate of a complex number, a plus bi, to find the conjugate, we simply negate the imaginary term. Not the real term, but the imaginary term. And so the conjugate of a plus bi would be a minus bi. The conjugate of 2 plus 3i would be 2 minus 3i. The conjugate of negative 4 minus 6i would be negative 4 plus 6i. And in doing this, the conjugate of negative 3i would be positive 3i. So the conjugate, it just changes the sign of the imaginary term, not the sign of the real term. So the conjugate of 4, it has no conjugate. It would simply be 4 itself. It doesn't change. It's only changing the sign of the imaginary term. Now there's some special things that happen as we begin multiplying conjugates, just like they do with our irrational numbers as we multiply those. But if we go through and we multiply, let's just start with our multiplication of our basic form. A plus bi times a minus bi. Now if we multiply these, we're going to get a squared. Then we get a negative abi. We get a positive abi. And then we have a negative b squared I squared. Now, if you notice, your middle terms drop out. They're opposites of each other. So we have a squared minus b squared I squared. But I squared's negative 1. So this is b squared times negative 1, which makes this a squared plus b squared. And if you notice, when we multiply the conjugates of our complex numbers, we end up with a real number. We don't have any i's, any imaginary terms. So if we went through, we've got 6 plus 3i times 6 minus 3i. Now, if you wanted to use the pattern that we just discovered, or that we just developed, then this is going to be 6 squared plus 3 squared. It was a squared plus b squared. And so that's going to turn out to be 36 plus 9, or 45. Now, if you're not sure about doing that, you can go through and do the multiplication. 6 plus 3i times 6 minus 3i. So we'll multiply our 6 times 6 would be 36. 6 times negative 3i would be negative 18i. 3i times 6 would be positive 18i. And 3i times negative 3i is negative I squared. Now our middle terms are going to drop out because they're opposites. And we're going to have 36. Now I squared's negative 1 times negative 9 would be a plus 9, which would give you 45. So if you can remember the little pattern, then when you multiply conjugates, it's just a squared plus b squared, then that works out fine. But if you're in doubt, just go through and multiply them, and you'll end up with uh, the correct answer. Let's look at one more. If we had 7 plus 2i times 7 minus 2i. Then according to our pattern, that's going to be 49 a squared plus b squared, which is 4, so we would get 53. And if you wanted to do it as the difference of two squares and saying it's the first term squared minus the last term squared, and actually have, doing it that way, you have 49 minus 4i squared, and then change your I squared. Negative 1 times negative 4 would make that 49 plus 4, or 53. So there's several different ways that you can go about doing this, using the pattern, using full multiplication, or using the difference of two squares. Okay, we will use our conjugates when we begin dividing. And to divide by complex numbers, you multiply both the numerator and the denominator by the conjugate of the denominator. Okay, to divide complex numbers, so we've got complex numbers, 5 plus 4i divided by 4 minus I. We want to divide these two complex numbers. Now, to do that, we're going to multiply both the numerator and the denominator by the conjugate of the denominator. Well, 4 minus I is our denominator. So the conjugate of that would be 4 plus I. And we know that just in basic arithmetic, whatever we do to the numerator, we have to do to our denominator also, or vice versa. So we're going to have to multiply both of these, so that all we have done is multiply it by 1. We haven't changed any value. Now, to multiply our numerators, we'll go through and just multiply like we would two binomials, use the distributive property. So we're going to have 20. Then we would have plus 5i. Multiplying them both by the 4i, we'll have 16i. Make that a better 16. We will have 16i. And then multiplying our last terms, we will have 4I squared. For our denominators, these are conjugates. And we just talked that whenever you multiply conjugates, you always get a real number. And in fact, you always get a positive real number. So let's use the pattern that we talked about. It's going to be a squared, which would be 16 plus b squared. Now in this case, our b is a 1. Uh, there's no number there, so it's understood to be a 1. That's our multiplicative identity property. So 1 squared is simply 1. Now, we want to combine the real parts and can combine the imaginary parts. So so far we've got 20, then 5i plus 16i would be 21i, and then we have 4i squared. Well, the I squared is negative 1 times 4 would give us negative 4 over 17. And now 20 minus 4 is 16 plus 21i over 17. Now there is one other way that this is written sometimes. It can also be broken up into the form of two separate terms. You've got your 16 over 17, that's your real part, plus 2i over 17. And you'll see it written that way. Sometimes you'll even see it written with the I out to the side. So you'll see it 16/17 plus 2/17 I. And it's written this way so that you can distinguish that this is your A, this is your real part, this is your B, your imaginary part. When we solve our quadratic equations, we'll often see it written in this form, especially if we're using the quadratic formula, then we'll end up with it written in that form. But either way is correct. Okay, let's look at another one that we'll divide. Let's say that we have 5i over 2 minus I. And so we're going to multiply by the conjugate, which would be 2 plus I. So we're going to multiply. Now in the numerator, we're simply multiplying a pure imaginary times a complex, but we'll use our distributive property, so that gives us 10i plus 5i squared divided by, these are conjugates, so it's our a squared, so 2 squared is 4, plus b squared, again b is 1, so 1 squared is 1. We end up with then 10i. Okay, I squared's negative 1 times 5 would be negative 5 over 5. Now, I mentioned earlier, this isn't the correct form to write your complex number in. We always write the real term first. So we're going to switch it around, and we'll have negative 5 plus 10i over 5. We want to check to see if we can reduce. Now, to be able to reduce, you've got to be able to divide both of these numbers, both your real part and your imaginary part, by the same thing you're dividing your denominator by. You can't just reduce one if you leave it in this form. And so in this form, all of these are divisible by 5. So we would have negative 1 plus 2i, and then divided by 5, which would simply be 1. If we divide each one of those by 5, it would be over 1, and that would be our answer. If we broke it up the way that I was showing you in the problem above, then you can see a little bit easier where this comes about. We have negative 5 divided by 5 plus 10i over 5, and then that reduces to negative 1, and this reduces to 2i. So if you're breaking it up in this way, it may be that you can reduce one but not the other. But if you're going to leave it in this form, then you have to be able to divide all of them. Okay, let's look at another example. If we have 3 minus 4i, divided by 4 plus 3i. Okay, we're going to multiply both the numerator and denominator by the conjugate, which would be 4 minus 3i. And we're going to do our multiplication. So we're going to have to use our distributive property. So we have 3 times 4 is 12. 3 times negative 3i is negative 9i. Negative 4 times 4 is negative 16i. Negative 4 times negative 3i would be a positive 12i. Divided by, since these are conjugates, it's going to be a squared, which would be 16, plus b squared is 9. Now combining, I didn't put my square out here, did I? Okay. Combining our like terms, we're going to have 12 minus 25i, and this is going to end up being a negative 12. I squared's negative 1 times positive 12 would give us negative 12 divided by 25. Well, 12 minus 12 is 0, so we have negative 25i divided by 25. Then we can reduce this and end up with negative I. And so we ended up with a pure imaginary number as we went through. Okay, we want to use these to get roots of some negative numbers and to do some simplification. And as we begin looking at these, we noted earlier, or if we look at this in our multiplication, if we were doing our properties, if we had 4i and we wanted to square it, well, we'll square the 4, which is 16. We square the I as I squared, which gives us negative 16. I squared's negative 1 times 16 would give us negative 16. Well, also, if we took negative 4i and squared it, well, negative 4 squared is 16, I squared, and that's also going to equal negative 16. So there's two numbers that when we square them, we end up with negative 16. So when we were looking for the square root of negative 16, then we need to know which answer to give. Do we give 4i because 4i squared is negative 16, or do we give negative 4i because if we square that, we get negative 16? So to keep any discrepancy there or anything where we're not sure, what we give here, unless we're otherwise stated, we always give what we call the principal square root. So we will give the positive value as our answer. So anytime we have the square root of a negative number, we're going to give the principal square root, the same as we do in our sets of real numbers, unless something is given so that we know that we would want the negative one. And to have the negative answer, we would have something along this line. We'd have the square root of negative 16, and so then that's saying we're wanting the opposite. So that's where we would end up giving our answer of negative 4i. But unless otherwise stated, you'll always give the principal square root of the number. So what we would define then, we'll define the square root of any negative number is going to be I times the square root of that positive number. And that will be our principal root. Now when we begin working with our numbers and we're doing our simplification for them, we always remove the negative from the radical first before we do any operation. If we had the problem, the square root of negative 18 minus the square root of negative 8, and we were going to simplify this. Well, we're going to go back and we can rewrite this as the square root of negative 1. And then we can simplify 18. Now, some of you'll know how to simplify it a little bit easier than others. It depends upon it. So if you're in doubt, you can always go back to your prime factoring of 18. 18's 2 times 9, and 9 is 3 times 3. So if we write it as a product of prime numbers, then we can do our simplification. We know that the square root of negative 1 is I, so that'll come out of the radical. The square root of 3 squared, or 3 times 3, is 3, so that comes out of the radical. And then we have the square root of 2. If we go over here to negative 8, well, again, that's going to be negative 1. Okay, 8 is 2 times 4, and 4 is 2 times 2. So if we write it as a product of prime numbers, then we can do our simplification. The square root of negative 1 is I. The square root of 2 times 2, well, the square root of 2 squared is 2. And then we're left with the square root of 2. Now, these are like terms, so we can combine them. We have 3i square roots of 2 minus 2i square roots of 2. So 3 minus 2 would be 1i square root of 2. And we can have our simplification. If we took the numbers, we want the square root of negative 27 plus the square root of negative 48. Okay, we have our 27. This would be the same as negative 1 times 3 times 3 times 3. If we need to do the prime factoring, the square root of negative 1 is I. The square root of 3 times 3 is 3 times the square root of 3. What's left? We were able to take the square root of 3 squared and the square root of negative 1. Now for 48, well, 48 is negative 1. And if you're, not as familiar with your factoring of 48, you may need to do your prime factoring off to the side where you can use the method. We know it's even. So 2 goes into 48 24 times. 2 goes into 24 12 times. 2 goes into 12 6 times. And 2 goes into 6 3 times. Some of you may have recognized that it's going to be 16 times 3, or and 16 is a perfect square. But if you need to do your prime factoring, then we have 4 2's and a 3. So as we do our taking our square root, the square root of negative 1 is I. The square root of 2 times 2 is 2. The square root of 2 times 2 is 2. Those come out of the radical because they're perfect squares. And then we're left with the square root of 3. So we have 3i square roots of 3 plus 4i, 2 times 2, square roots of 3, which gives us 7i square roots of 3. All right. We're going to stop this right here. We still have a few more things, and I'll continue it in part 2. But as far we're kind of running out of time for what you can download easily. So we're going to go ahead and stop here. We'll pick up in part 2, and we'll just have just a little bit then to finish with.